Greetings and welcome to second lecture on fluid kinetics. This lecture we will discuss some numerical of determination of velocity and acceleration. In previous lecture, we have discussed the two approaches of determination of the flow field. That means the determination of velocity and acceleration. So we'll see the numerical part in this session. So first numerical, that is find the velocity and acceleration at a point. So the three space coordinates are given. That is 1, 2, 3. After time 1 second, or three-dimensional flow given by the three components. That is u is equal to yz plus t, v is equal to xz minus t, and w is equal to xy. So three components of velocity is given. As the three components are given, means this is a three-dimensional flow. So at the given quantities, the three-dimensional flow field is given by u is equal to yz plus t, v is equal to xz minus t, and w is equal to xy. So velocity at point 1, 2, 3. Velocity at 1, 2, 3 after 1 second is calculated is found. So u component velocity by putting the y, z, and t values, it comes around 7 meters per second. V component velocity by putting the value of x, z, and t, so it comes around 2 meters per second. And w component by putting the value of x, y, that comes around 2 meters per second. So the resultant velocity vector is given by 7i hat plus 2j hat plus 2k hat. Its magnitude is under root UVW. It comes around 755 meters per second. Hence, the resultant velocity is given by 7.55 meters per second. In order to calculate acceleration at 1, 2, 3, we have v is equal to this is velocity vector. The total acceleration is given by dv by dt, that is equal to dabba v by dabba t plus v bar into del v bar. So acceleration along x direction, the total acceleration u dabba by dabba v plus p into dabba v by dabba x plus w into dabba v by. So this is in conservative form. This is in conservative form. This is non-conservative. Now, instead of the acceleration along x, y, and z directions, x instead of capital V is replaced by x component velocity, gives us x component acceleration. And by differentiating u with respect to x, it is 0. Differentiating v with respect to u with respect to y, it comes around xz minus, that is v component, xz minus t, and this differentiation is z, that is dabba u by dabba y, plus differentiation of u with respect to that w component, that is differentiation of u with respect to z is y, and dabba u by dabba z is y. W component is there, that is xy. So xy into y plus dabba u by dabba t is 1. So by putting all the coordinates, we get the value of x. Similarly, we can calculate the acceleration along y direction by differentiating v component with respect to x, y, and z, and t. And putting the values, we get 22. and acceleration along z direction. Similarly, by differentiating w, that is xy with respect to xy and z, and w with respect to time as well, it comes around 16. So it's only a differentiation part that you can easily understand. So acceleration along x, y, and z direction, similarly we can obtain. And the acceleration vector, so this is acceleration by putting the value of ax, ay, and z. We get acceleration. So, velocities and accelerations we can obtain this way. So simply by giving the values of u, v, and w, by using the expressions of ax, ay, and z, calculate the acceleration. Second numerical, where the velocity along the center line of the nozzle of length L is given by, so this resulting velocity is given by this expression, where V is equal to velocity in meter per second, is the time in seconds from commencement of flow. X, that is equal to distance from inlet to the nozzle, is measured from the inlet to the nozzle. Calculate the local acceleration, convective acceleration, and total acceleration. When time is 6 seconds, x, that is equal to 1 meter, and the total length, that is 1.6 meters. So first, the velocity along this center line of the nozzle is given by this expression. So, local acceleration. So we derive this v with respect to time. It becomes 2 into bracket 1 minus x by 2l bracket square. Then by putting the values of t is equal to 6 seconds, x is equal to 1 meter, length is 1.6 meter, we get the local acceleration is gamma v by gamma t, 945 meter per second square. As convective acceleration is given, that is along x direction only, because there is only unidirectional flow is given. So acceleration is v into gamma v by gamma x. There is no variation given along y and z direction. So only one component of convective acceleration is there, v into gamma v by gamma x. So v is already given. Gamma v by gamma x. So this is v. Gamma v by gamma x. 2t into 2, that is derivative of this with respect to x. So 4t bracket 1 minus x upon twice L. And the differentiation of x upon square. So simplification, we get this expression. Then at t is equal to 6 seconds and x is equal to 1 meter, get the convective acceleration, which is negative towards the negative x direction, that is minus 29.24 meter per second. The total acceleration is the addition of both, that is local plus convective. So the total acceleration is minus 28.295 meter per second. Total acceleration is negative, that means the acceleration is taking place in negative x direction. So this way we can calculate the local convective and total acceleration. Now in this case, there is unidirectional flow is given because there is no y and z coordinates. Form of convective acceleration is reduced to unidirectional. By differentiation, we can estimate all the components. So That's it. This is the numerical part. At the end of this particular session, you should be able to apply the expression of velocity and acceleration as per the Euler's expression.